So we're going to pick up with section 22.1. We're still talking about alkanes, and there are some key things to bring up when it comes to alkanes, and that's in reactions. There are a few different types of reactions that are really common with alkanes. Now, there's many more out there that we're not going to touch on, but there's some important ones, and some of them you should already know, right? You should know, for example, how to balance a balance a combustion reaction. Remember, a combustion reaction, especially with an alkane, so you have an alkane that reacts with oxygen to form carbon dioxide and water. And this is, by the way, a redox reaction of sorts. If you look at the oxidation state of the carbon in methane, it should be -4. So -4. But in carbon dioxide, the carbon is +4. Right? Oxygen, of course, is 0 in oxygen gas, and it's -2 in both oxygen gas and in water. Of course, the hydrogen is +1 on both sides of the chemical reaction. Right? So combustion reactions, the reason they pack so much punch as far as energy is because they're oxidation reduction reactions, and those tend to have a lot of energy associated with them. So that's combustion. There's another type of chemical reaction that occurs where if you take a hydrocarbon, and we're going to take and keep it as simple as something like methane, and you have that methane gas in a container with chlorine gas, and if you just have one equivalent worth of chlorine, right? One stoichiometric equivalent. So if you have 1 mole of methane, you have 1 mole of chlorine. And that reaction doesn't go by itself, but it does go if you shine UV light on it, okay? So this is sort of saying UV light. And the UV light will cause a reaction, and this is something you'll study, what's called the mechanism for this reaction, which is similar to mechanisms we've done before, only you'll really see when you get into organic chemistry how the electrons move around in these molecules. But if you shine light on this chemical reaction occurs such that you replace one of those hydrogens with a chlorine and you make HCl gas, okay? And so you can do that this one step at a time. So one equivalent of chlorine gas will produce one equivalent of chloromethane, okay? If you add a second equivalent of hydrogen gas, you'll make a compound that's called methylene chloride or dichloromethane. If you add 3 equivalents of chlorine gas, you'll make trichloromethane, which is also called, so this is chloroform. Okay, it's an organic solvent. This right here is dichloromethane, or also called methylene chloride. Right, and so that's not the, these aren't the IUPAC names, these are more common names for these. But if you add a 4th equivalent of chlorine, right, you'll actually make carbon tetrachloride, which is something that's really not good, and it's hasn't been around for quite a while, okay? Or tetrachloromethane, if you will, also, right? But chloroform is a solvent that used to be used as an anesthetic, not so much anymore. It's pretty dangerous as an anesthetic. This, right, it's what everybody in the mystery things. It's what people use to soak in a cloth in, and it knocks people out, right? Another type of reaction that you'll see with alkanes is called a dehydrogenation reaction. Not dehydration, that's a very different thing, right? But dehydrogenation or dehydrogenation, okay? That kind of a reaction is a reaction that you literally take away or eliminate, right? It's called an elimination reaction. Okay, it's an elimination reaction. You're going to eliminate, right, the hydrogen gas. So by reacting something like ethane with a catalyst, right, at a high temperature, you're going to form a double bond, right? In fact, in this case, you're going to form an alkene, okay? Which in this case, the alkene is ethylene. okay? And that alkene is the result of the elimination of hydrogen gas, okay? And so this is, again, it's a chemical reaction. It's an elimination reaction called a dehydrogenation reaction, not to be confused with dehydration, where dehydration is the elimination of water. Dehydrogenation is the elimination of hydrogen, right? So dehydrogenation. And those are some of the reactions that you'll see with alkanes. And so hopefully when you get to organic chemistry, you'll remember a little bit of this and you won't, you know, it'll put you a leg up on everybody else. Now, the next thing that we're going to get into in section 22.2 is alkenes and alkynes, okay? Alkenes are going to be hydrocarbons with a double bond, okay? So we'll talk about their structure in a little bit, but when we look at alkenes, right, the big difference between alkenes and alkanes is that we have now a double bond, right? They're still hydrocarbons, but now we have this double bond. So if you had, so C2H6, right, is the alkane, right? H6 is the alkane. Try that again. There we go. Which has a structure like so. Right, which is, this is ethane. Okay. Well, then C2H4 will be the alkene. Okay, and C2H4 has a double bond between the carbons. Okay, this will be ethene or ethylene. Right, but really it's ethene is the name there, right? And so what we're doing is now we have, for these chemical compounds, the only difference really for most of them is going to be the, at least nomenclature wise, the double bond, right? So we have the CC double bond, okay? And so your overall chemical formula now is CnH2n. So this is gonna have the same chemical formula, generic chemical formula, as the cyclic hydrocarbons does. Okay, so in the cyclic hydrocarbons, we had 2 hydrogens fewer because the 2 carbons were connected. Now we have 2 fewer carbons, excuse me, 2 fewer hydrogens because you have a double bond between 2 of the carbons. Okay. If you have alkynes, alkynes are, right, now we're going to switch the ending to a YNE, and they're going to have a triple bond. So if we had the alkane is C2H6, the alkene is C2H4, the alkyne will be C2H2. Okay, and so it'll be C with a triple bond, C with the hydrogens bonded to it. And so this particular molecule would be ethyne, but it does have a common name of acetylene. So if you've ever used an acetylene torch or know someone who has in something like welding, right, an acetylene torch, you're burning this particular molecule. And so that's the name of it. The overall formula for hydrocarbons with triple bonds is going to be CnH2n -2, okay? And so a couple examples. So if you have C3H6, that'll be propyne or propylene. Okay, so like polypropylene is a polymerization of propylene, and we'll look at polymers a little bit later. But this will be C double bond C bonded to a C, and we'll talk about nomenclature of these a little bit here in a bit. Okay, or you can say propyne, which would be C3H4. Ah, shoot, I totally did this wrong. This should be propene up here. Ah, what did I do? E and E, this should be propine. Sorry to confuse you on that one. That's the E and E ending and the propylene there. So propine would be C, H, C, C. Okay. So there's your overall example of propine. So you've got now a triple bond, right, between the carbons, and that gives you the Y and E ending, okay? And so when we look at these, one of the key things to remember is bonding. So if you think your way back, all the way back to Chem 101, where we looked at the hybridization of the different alkanes. So if we take and look at something like so propane versus propene, or propylene versus propine. So C3H8. So what we'll do there is we'll just draw out this whole structure. So remember in Chem 101, we went and identified what are the types of bonds and what orbitals do they come from, right? So when it comes to the hybridization of the carbons, all of the carbons will be sp3 if you just have alkanes, right? So this is propane. Right, they're all sp3 hybrid. So if you were to look at a CH bond, right, a CH bond here would be a sigma bond between a carbon sp3 orbital to a hydrogen 1s orbital. Or if you were looking at the CC bond, that would be a sigma bond between a carbon sp3 and another carbon sp3. Right, those are the possibilities that you have there. But when you have an alkene, now you have the possibility of having either sp3 or sp2 hybrid carbons. So in the case of something like propene or propylene, so C3H6, you now have C double bond C to a single bond C. Draw in all of our hydrogens. Oop, too many bonds to that middle one. Okay. And so here we have now the CH bonds are going to be two possible configurations. You've got the CH bond here. Actually, you know what? I'll do this different. Give me a second. Okay, we'll do our first CH bond is going to be one of these ones, right? Where you have a sigma bond to a carbon sp2 hybrid, right? Remember, the steric number of this carbon over here is 3, therefore it's sp2 hybridized. So that to hydrogen 1s. The other carbon CH bonding motif, right, is going to still be a sigma bond, but now it's going to be one that is going to be represented here. And so that you can have a carbon sp3 orbital bonded to a hydrogen 1s. And then it comes to the carbon-carbon bonds. If you have a carbon-carbon single bond, which is this one here, that's going to be a sigma bond, because remember, all of our single bonds are just sigma bonds. Here you have a carbon sp2 bonded to the carbon sp3. And then you have this double bond here. Okay, so on that double bond, right, this is our carbon double bond carbon. There we have a sigma bond and we have one pi bond. So the sigma bond is going to be formed from, well, both of the carbons are sp2 hybridized. So carbon sp2 to carbon sp2, and the pi is carbon, it's the unhybridized p orbitals. Hopefully you guys remember some of this. All right, so 2p, you can label it X, Y, or Z, doesn't matter as long as it's the same as the next carbon's p orbital, okay? So in both of those, so now we have these other possibilities, but the carbons themselves are now either sp2 or sp3. If you look at an alkyne, right, so something like propyne, C3H4, here we now got our triple bond. Okay, do that right there. Yeah, okay, good. So we've got our triple bond there. We've now got our different types of CH bonds. We can have a CH bond that is back over here, right? That is an sp hybridized carbon. And so you can say, well, that's a sigma bond between a that's a sigma bond between a carbon's sp hybrid orbital to a hydrogen 1s orbital. You've got your CH bond here, right there, that is a sigma bond from the carbon sp3 orbital to a hydrogen 1s. You've got a carbon-carbon single bond there, which is a sigma bond, carbon sp, because that middle carbon is sp hybridized, right? There's only a steric number of 2, which means it's going to have sp hybridization, to hydrogen, carbon, just throwing myself off here. So to the carbon sp3 orbital. And then we have our other carbon-carbon bond, this carbon-carbon triple bond. Come on. Hand is not doing what my brain is trying to tell it to do. There we go. 1, 2, 3, carbon-carbon triple bond. On this one, you have a sigma bond and 2 pi bonds. The sigma bond will be just the carbon sp hybrid orbital bonded to the carbon sp hybrid orbital. But each of those carbons has 2 unhybridized p orbitals. So to make the first pi bond, we'll pick one of those p orbitals. So carbon 2px bonded to the carbon 2px. And then we'll pick the carbon 2p, let's say y, say our bonding axis between the 2 carbons is the z-axis. So we'll have the carbon 2py bonded to the carbon 2py. So hopefully you remember some of this stuff from Chem 101, and you can identify the orbitals that are involved in the bonding in any of these compounds. Okay, and so there's just a preview of that. Now, something to bring up, we talked briefly about it in Chem 101, but it becomes more important in Chem 102, right, is how these, what this means for the bonding, okay? So if we have something like ethane, okay, and we just have this single bond between the 2 carbons, right? That single bond, right, means you have overlap just right in the middle there. And it means that there's an ability to rotate, for that bond to rotate. So you can take that bond, those methyl groups that are attached to each other rotate, okay? And so they're not locked in place in any way. They can rotate around that bond. And so that allows for that molecule to have certain properties because of that rotation, okay? But when you only have a single bond or a sigma bond, that sigma bond can rotate. So when you have something like ethylene, where you have now you still have the sigma bond in the middle of something like ethane or excuse me, ethylene. But then you have this pi bond that forms from the overlap of the adjacent 2p orbitals. And so, here's our picture of that is up here, where we really see this pi orbital, right? So the pi overlap of those 2p orbitals to form a pi orbital, right? And remember, this is just one bonding orbital there, and I'm going to shade this in for the sake of reminding you this, right? That orbital, when you have the side-to-side overlap, it basically stops you from being able to rotate that bond. So a way to look at it, if you will, if we say, hey, here's my highlighter pen, put that in, there we go, format in front of the board, right here. So you can see that, that's my sigma bond. And then the orbitals, the overlap of the orbital densities for the pi bond is gonna be my black pens here. I know it's a little hard to see if it's closer. If you just have the sigma bond and only a sigma bond, right? This can rotate, sort of like the pen cap, it can rotate. But when you have the pi bond, where you have orbital overlap above and below that bonding axis defined by the sigma bond, then this molecule, in order for those to stay intact, this molecule can no longer rotate around that bonding axis. And so it essentially locks into place the position of those atoms that are bonded to the carbons, okay? And so what'll happen is, it means that you have now very distinct positions on in a molecule with a double bond. Okay? And we're going to talk about that when we look at isomers here in a minute. When it comes to the orbital bonding in a molecule like acetylene, where you have a triple bond, now you have a couple of orbitals. Both of these, the p orbitals will overlap. So that p orbital overlaps there in the red, right? So remember, that's just one bond. And then I'll use green to illustrate the other orbitals that are overlapping. So there's the other ones, right? So this will be your py from each, right? Your py and your px. Oops. Right here, and your px. So you almost have, because of how those p orbitals overlap, you almost have this barrel-shaped orbital or electron density going around the bonding axis, forming those pi bonds. Now, in the case of something like acetylene, where you have a triple bond, there is, since the carbon centers are both linear, it doesn't matter where they're at. It will when you start to see how the alkenes bonding matters, okay? So when it comes to naming, the biggest thing is, the difference is we're going to change the ANE to either an ENE or a YNE. When we start numbering, we're going to now number the chain beginning with the side that will give the lowest number for the double or triple bond. So now we're going to number our chains a little differently. Whatever side is going to give the lower number for the double or triple bond is the side that we're going to start numbering on, okay? And then we're going to have this other thing, these cis-trans isomers. And this is going to be for alkenes, okay? So a reason for this, if we were to draw in a molecule, so here's my molecule, it's 1, 2, 3, 4, 5, 6, so it's a hexane. And here's a double bond in hexane, okay? And so we could number it in one of two ways. We could either number it from the left or from the right. So we can number it 1, 2, 3, 4, 5, 6. Or we could number it, there we go, from the other side. 1, 2, 3, 4, 5, 6. Okay. The way that we're going to do this is we're going to take the top one, because you can either get the 2 or the 4 position for the alkene. You want that one because that's a smaller number. And you're going to use the smaller of the two numbers anyway so if you consider 2 versus 3, the way that this would be done is this would be written as 2 hexine. But there's this other thing for before the, hexene. That's an ene. Why do I keep doing that today? Too many things in my brain that are not working. Come on. Finally. There we go. Ene. There we go. There's another thing we have to add to this, though, is either cis or trans. And so there's going to be a cis or a trans out front. I'm going to tell you on this one right now. This is, based on how this is drawn, this is a trans to hexene. And that's based on this double bond and how the pieces on either side of it are drawn, okay? And so we'll get more into that now. In particular, with butene, okay? So with butene, think about it this way, right? This is a C4H8. And so if we think about the possibilities here, right, we've got carbon bonded to carbon, bonded to carbon, bonded to carbon. We're going to put initially a double bond between the first and second carbon. And then we'll fill in all the rest of our hydrogens. Okay, this one right here will be 1 butene, right? Where the 1 specifies where the double bond is, the E and E specifies that you have the double bond, okay? On this one, this doesn't actually matter where it's at, and you'll see why in a second, right? It's mostly because both of the things on this are these are both hydrogens, right? So there's no cis-trans isomerism. So there are no cis-trans isomers. Right, if they're the same. Okay, and so that's a key here. However, there are a couple other ways we can do this, right? We can now take and say, well, here's 1, 2, 3, 4 carbons. What if we put the double bond in the middle? Now, when we put the double bond in the middle, I'm going to start out by just drawing in my hydrogens on the other carbons. So we've got 6 of our 8 hydrogens that'll be drawn in first. What does matter here, and you'll start to see this, it's actually a little easier to see when we depict the bond angles more like what we should. But basically, I can draw both of these hydrogens in on the same side of this double bond, and that makes a difference because this is one way of doing this, okay? But I can also draw this molecule such that one of those middle hydrogens is on the other side of the double bond. So I'll draw it in that way. Oops, C, double bond, C. And so then I'll draw it in sort of with perspective drawing so it's easier to see this. Okay, so here's the main backbone. If I now go here and put one hydrogen on one side and the other on the other side, these are 2 different molecules. Okay, and it's really easier to see sort of in a structural formula. So if I take this double bond and I say, okay, here's my double bond. What I'm going to do with this double bond, I'm going to put a line through the 2 carbons. Come on. Okay, through these 2 carbons. These are just the middle carbons. So here's a kind of dashed line through that. Okay, it goes directly through those 2 carbons. And then what we're going to do is we're going to place our hydrogen or methyl group. Here we go. So here are the bonds for these things. Place our hydrogens or methyls off of there. Now these two hydrogens are on the same side of this little orange line that's separating them. So I'm going to put them on the same side, H and H. And when I do that, I need my CH3 and my CH3 here, right? Those two, they're on this, the CH3s are on the same side, okay? Notice they're on the same side of that double bond, assuming you're drawing a line through the double bond, the carbons that are involved in the double bond. They're on different carbons, but they are on the same side of the double bond. Remember, this double bond cannot rotate. It's stuck in place, so it matters. If we go to the other one, and I draw in initially my carbon double bond first, and then I put in my line through the carbons. Okay, what I can do here is I can illustrate such that I've got my hydrogens on either side. So here's one hydrogen, here's the other. And so my methyl groups, the CH3 there, are on opposite sides. Right? Those are on opposite sides of the line. Okay? And so if they're on opposite sides, we're going to give it a prefix of trans. Okay? If they're on the same side, we're going to have a prefix of cis. Okay? And so when we have this, if I were to do the line angle drawing, well, so what we'll do is we'll take and look at the name of that one, right? So cis and trans. So it's a 2-butene because we have 1, 2, 3, 4 for the butene. And on both of these, the carbons, we have 1, 2, 3, or 4. Right? And so on both of them, the double bond is going to be starting at the 2 position, the lower value, right? So it'll be cis as my prefix, 2-butene. On the other one, it's still again 1, 2, 3, 4, but now the carbon, the methyl groups are on either side of that line, and so it becomes trans 2-butene. Okay, here's what that one is. Okay, there's one other isomer for this. Okay, and that other isomer is neither cis nor trans. So the cis and trans I thought would take up more space than they did. The other isomer that we have for butene, apologize for the organization here, is where you have the carbon double bond off of the first carbon. And then both of the methyl groups are off of the next one, which means you have 2 hydrogens off of here. And so this is another isomer of butene, but it's not named as a butene because it doesn't have a 4-carbon long chain. So you'd have 1, 2, or 3. So this would become a propene. Okay. And you would have a methyl group, okay? But in particular, the propene, right, is at from the 1 position. So here, and the methyl group is at the 2 position. So it would be 2-methyl, 1-propene, okay? And so the 1 specifies where that, actually, you wouldn't even need to write in the 1 on this case. So it would be 2-methyl propene, right? Because even if the 1 is on the other side, you don't need to write it in because it would still be the same thing, okay? And so this molecule would be 2-methyl propene, okay?
Do you need to use a prefix at any point, like to specify di, or no?
There is no di on this, right? So we're saying our longest carbon chain is here. if you were to have two methyls in here somewhere or on a molecule, yeah, you would have to use those prefixes if you have a bunch of them. Right? So that would be your isomers of butene. Okay, and so the idea here is now you have to specify cis-trans isomers, in particular when you have a double bond, and on either side of, so if you take the two carbons in the double bond and say, we're going to draw a line through them, and above and below that line, right, is going to distinguish whether we have cis or trans isomers, right? If they're on the same carbon, right, it's not cis or trans, right? Because the methyl or groups are on the same carbon, right? Okay, and that's a key there. And so that's really it for today. We'll deal with alkynes later. What you've got for today is basically you're getting some more practice with some things that we've done already, okay? And so what I'm going to do is I'm going to stop recording here and we'll talk about the lab a little bit, and then I'll let you get to it.